Hello everyone. In this video, we're going to do the homework take-up from the previous lesson, which is on properties of planes. Okay, and there's 6 questions that I received via email to go over. So we're going to start with 6A on page 459. So this one says determine the scalar equation of this plane. Okay, and the equation is there. So this one is similar to example 2 from the actual note. Just we've actually been given a little more information up front. Okay. But again, to show what's going on, I'm going to draw a quick little picture before I get into determining the equation. Okay. So they've given us all this information about the plane. Okay. So if that's my plane, okay, I have this point. Okay, that would be my 3, 7, negative 5. Right. There's a point on the plane. Okay. And these other 2 pieces are my direction vectors, right? That could be my vector with S, and this could say be my vector with T. Okay, so I have a point on the plane. I have the 2 direction vectors. Okay, so to get the scalar equation, I need a normal, okay, which is a vector that is perpendicular to the plane, which means it would be perpendicular to both of those other vectors. So my first step is going to be find the cross product of S and T. Okay, so I shouldn't say S and T, but right, the direction vectors associated there. So N is equal to 1, 2, negative 1 crossed with 1, negative 2, 3. So I went that on the side, right, and I got 4, negative 4, negative 4. Okay, now as we mentioned in the last video, to make my life easier, this is a direction vector. I notice I can make this a little simpler. Okay, they're all divisible by 4, so I could use the vector 1, negative 1, negative 1. Right, that would just be a shorter vector here. Okay, that's my normal. And now we can figure out the scalar equation from there. So again, my form of the scalar equation is AX plus BY plus CZ plus D is equal to 0. Okay, I fill in my normal, so I have a 1 and a negative 1 and a negative 1, and I fill in my point, 3, 7, and negative 5 plus D is equal to 0. So let's see, that's 3 minus 7 plus 5, so that's 1 plus D equals 0. And so D equals negative 1. Okay, so that makes my equation X minus Y minus Z minus 1 is equal to 0. On to the next one. Okay, number 7A from page 459. Okay, write the scalar equation of this plane here, which is currently in the parametric form. Okay, so for this one, it's actually very similar to 6A. Okay, just I'm going to put it back into vector form, and it will help me see what I have to do. Okay, so if I want to rewrite this in the vector form, right, my equation is xyz equals, okay, that first part is going to be my point. So that's 3, 1, 5. Okay, this next section with S, that's going to be my first direction vector. So plus S, negative 2, 3, negative 1, okay, plus T, and I have 2, 1, and 2. Okay, and now that I'm in this form, okay, it's going to be the exact same steps as what we just did, taking up 6a. Okay, to find my normal vector, I'm going to do the cross product of my two direction vectors. So 2, 3, -1, crossed with 2, 1, 2. Now, I'm taking the back of the book a bit. I just noticed that I missed a negative sign here. This is supposed to be -2. Okay, so when you do the cross product of those two things, okay, you get -5, -6, and -8. Okay. And again, to make my life a little bit easier, when I get down to the calculations, okay, I have 3 negatives there, so let's just flip that around to positive. Okay, because that's just going in the opposite direction, and it'll still be perpendicular to the plane. Okay, now that I have my normal, I can use that to build my equation. So ax plus by plus cz plus d equals 0. So my normal, I have 5 and a 6 and an 8. Okay, and my point was 3 and a 1 and a 5 plus d equals 0. So 15, 6, 40. So I've got 61 plus d equals 0. So d is -61. Okay, so I've got 5x plus 6y plus 8z subtract 61 is equal to 0. Okay, number 8a. Write the vector in scalar equation given the plane is perpendicular to this line and includes this other point. Okay, and again, I think this question was kind of similar to example 3 from the note from the previous day. But if we draw a little picture, it says it's perpendicular to this line here. So whatever my line looks like, okay, it's perpendicular to that line, and my plane is going to include a point over here. Okay, now it wants us to do both vector and scalar forms. So with the information we're given, okay, I know that this right here is going to be my normal because that's the direction vector that's perpendicular to the plane, and I have a point. So I should probably start with the scalar equation of the plane. Okay, so we're going to start with that. So once again, we have ax plus by plus cz plus d equals 0. Okay, so my normal is 3 and 5 minus 3. Okay, and my point is 4 minus 2 and 7 plus d equals 0. So let's see here. 12, -10, -21. So we got 2 take away 21, so -19. -19 plus d equals 0. So d is equal to 19. So my equation is 3x plus 5y minus 3z plus 19 is equal to 0. Okay, we've got the scalar form. So the question is now, how do I go to vector form from here? Okay, and we haven't directly talked about how to do this. But let's think about what we need, right? To create the vector form, I need a point, okay? And I already have the point. That was this 4, -2, 7. Okay, so let's start with that. Okay. X, Y, Z, plus. Okay, then I need to have two direction vectors. So S times something, and T times something else. Okay, now I don't have any direction vectors yet. Okay, so there's a couple things we could do here. One way we could do this is to note that, well, whatever the direction vectors are going to be in this plane, they have to be perpendicular to the normal, right? Like if my vector goes this way, it's still going to be perpendicular. If it goes this way, it's still perpendicular. If it goes that way, it doesn't matter which way. So I just have to find a couple of different vectors that are perpendicular to the normal, and they should lie in that plane, because anything that's perpendicular to that vector should be in the surface of that plane. Okay, so that would be using the trick where, we'd set up the dot product and say, okay, I've got 3, 5, -3 dotted with something. So maybe I'll make up some numbers here. So maybe I would say, I don't know, I could start with a 0, and to make the numbers work out, I'm going to say 3. Okay, and then I could do 5. Okay, because if I do the dot product of those two things, okay, I'd get 3 times 0, I'd have 0 plus 15 minus 15, and that's equal to 0. Okay, so this should be a direction vector that works. Okay, that's one way we could do it. Okay, another way we could do it would be to generate some additional points on the plane. So like try to create 2 more points and then run direction vectors between those 2 points. Okay, so if I go back to the scalar form of my equation, okay, I could, again, similar idea to this, I can just pop in a couple of numbers, okay, and see what the third one comes out to, and then go from there. Okay, the fact I have a 19 sitting here doesn't make this particularly nice to work with, but we'll play with it and figure something out. Okay, so for example, let's see what might work here. So thinking ahead here, if I add 6 to 19, I get 25. So that could give me some nice numbers to work with. So for example, if I let's let x equal 0. So I have 3 times 0 plus 5 times 5 minus 3z plus 19 equals 0. Okay, change my mind. I want -5 in there, so I get some nice numbers. Okay, so I've got 0 there, so -25 minus 3z plus 19 equals 0. -25 plus 19 is -6. So when I bring that around, it's going to be +6. So z is -2. Okay, so the point, this is not a vector, this is a point. The point 0, -5, and -2, okay, should be on the plane. Okay, to get another point, I'm going to make z equal to 0. So 3x plus 5 times -5 minus 3 times 0 plus 19 is equal to 0. Okay, so now when I run this through, it'll be same process as above, but I'll come out with x is equal to +2. So another point is 2, -5, and 0. Okay, so that with the point I already had, I had 4, -2, and 7. Okay, I can work out two direction vectors. So let's say if I called this one up here, this would be like my point A, and this is B, and this is C. Okay, so the vector running from A to B would be -4. 5 take away -2 is -3, and -2 take away 7 is -9. Okay, so there's one direction vector. Okay, and for C, I can now do vector A to C, which would be -2, -3, and -7. Okay. And a quick check here, these are definitely not scalar multiples of each other, so they're going in two different directions, so we'd be good. So this could be -4, -3, -9. This could be -2, -3, -7. Okay, and there are literally an infinite number of possible ways I can set up these two direction vectors, right? If I go back to my picture, right, I could put 2 points anywhere on this plane and create 2 more vectors running between them. Okay, so there's no one solution to this. Okay, a quick way you could verify if you did it right would be to take the cross product, right, of your two direction vectors and see if they give you the normal vector that we had above, right? When I do the cross product and maybe do some reducing, I should come back to 3, 5, and -3 if it's right. Okay. Okay, number 10a, determine if the planes are parallel, perpendicular, or neither. Okay, again, we haven't directly talked about this, but let's think about what's going on. Okay, if the two planes were parallel, so something like this in space, okay, then their two normals would also be parallel. They'd have to be running in the same or opposite directions. Okay. If the planes were perpendicular, so this is going to be a little hard to draw, but something like this. Okay, they meet at a right angle. Okay, well, when I tack on the normal vectors, right, normal vector, they would also meet at a right angle. Okay, and the reason I'm highlighting the normal vectors is because, well, I'm in a scalar form, so I can see what my normal vectors are. Okay, normal vector for plane 1 is 4, -5, and 1. Okay, and the normal vector to plane 2 is 2, -9, and 1. So now let's think about the testing. Okay, if they were parallel to each other, okay, that would mean they would have to be scalar multiples of each other. Okay, so looking at my vectors, okay, if I double 2, I get 4. If I double -9, I do not get -5. Okay, so these are not scalar multiples. So they are not perpendicular. Sorry, not parallel. Okay, perpendicular. Okay, how do I check if two things are perpendicular? Well, we go to our old friend, the dot product, okay, and see what happens. So if I do n1 dot n2, let's see, I'm going to have 8 plus 45 plus 1, okay, and it's definitely not 0. So therefore, these are not perpendicular. Okay, so not parallel, not perpendicular. So the answer to this question is they are neither. Okay, I think 10C was requested as well, but now that you know what the tests are, you can run that through and see what that comes out to. Okay, number 17a, determine the angle between the two planes. Okay, and this question, I know, has a big preamble that I didn't write down here, but it gives you a good hint as to what's going on. It says, since the normal vector to a plane determines the orientation of the plane, the angle between two planes can be defined as the angle between their two normals. Right, so again, what that's talking about, and bear with me with the drawing here. Okay, right, if there's plane one, okay, and let's say I have plane two, like this, slicing through there. Okay, it's really asking me for the angle between the planes, right? What's this angle kind of in here for the pitch? Okay, what the preamble is saying, well, if I compare the two normals, right, here's the vector perpendicular to this one, here's the vector perpendicular to this one, that angle running between the two normals should be the same as the angle between the two planes. So I really need to find the angle between the two normal vectors. Okay, so how do I do that? Well, we've got to dig back into our toolkit here, right? We know that for the cosine of an angle, okay, that is equal to the dot product of two vectors, okay, over the magnitudes of the two vectors. Okay, and the two vectors I'm comparing are the normals here, right? So my first normal 1, is 3, 2, and 5, and normal 2 is 4, -3, and -2. Okay, so dot product of those two things is going to be 12. Take away 6, take away 10. Okay, and the magnitude of the two vectors, let's see here. The square root of 38 and square root of 29. Okay, so when I run this all through, I got negative 0.1205 approximately. Okay, and then when we do the cosine inverse of that, we got 96, okay, 96.9 or about 97 degrees. Okay, and we're good. Okay. Now, as a quick note here, okay, the way I drew those two planes at the top, okay, that looks like it should be an acute angle. Okay, I guess just the way these two vectors lined up, I ended up getting the obtuse angle going this way. Okay, but it still could be considered the angle between the planes. Okay. All right, last one, number 18. Okay, for what value of k are the planes parallel, perpendicular? Okay, so I'm glad we took out number 10 because that's basically the same kind of question, right? Starting with parallel, okay, if they're parallel, they would have to be scalar multiples of each other. So my first normal vector, so normal 1, is 2, 6, and -2. Okay, normal 2 is 5, -15, and k. So kind of by inspection here, because this 2 became a 5, this -2 should probably become a -5. So most likely it's going to be k equals -5. I just want to verify that it's the same thing here. Okay, so to go from 2 to 5, that's times 2.5. Okay, if I multiply 6 by 2.5, I do get, oh wait, that's interesting. Unless I copied it down wrong, it looks like that doesn't work. Okay, I copied that down wrong. This is a plus, because I can't have that sign switch. Okay, so it does work out. So yeah, by that, k would have to be equal to -5. All right. Okay, for perpendicular, okay, we would need to do the dot product and solve it for k. So if they are perpendicular, then n1 dotted with n2 would have to equal 0. So for n1 dotted with n2, I have 2 times 5. So that's going to be 10. 6 times 15, 90, minus 2k is equal to 0. So 100 equals 2k, and k should equal 50. Okay, so if they're parallel, k is -5, and if they're perpendicular, k is equal to 50. Okay, so that's our first homework take-up video. Okay, and that's going to be the end of this video, and there's going to be a separate one with the actual lesson. Thanks for watching.